So I'm slightly surprised that a conference organized by David and Alexei, I'm the first person the second day to talk about descent obstructions. But okay, so I'm gonna have to define. So I want to say a little bit about descent obstructions, just informally, because it's just motivation for what comes next. But so if you have a map of algebraic varieties. Okay, so let me fix my field. So, well, to begin with, it would be any field, but K is going to be, for the purpose of the first 5-10 minutes, it could be a number field or a function field in one variable with constant field little k. And this is going to be the setup that I'm going to stick to for the rest of the talk, but for the first 10 minutes could be a number field as well. So let's say this is a G torsor, or G some algebraic group or something. So the map is a torsor. So the fibers are G torsors. So there's an action of G on each fiber. And so for each point P in xk, then the inverse image of P is a G torsor. So this guy is an element of here, and we can decompose the rational points of X as a disjoint union over the classes in this H1 that describe the specific torsor that the fiber represents. So how I'm going to write this? I can write it as pi sigma y sigma of k, where the pi sigmas, C. Pi c is y c to x is a twist of pi from y to x given by c. Yes, I'm going to be living dangerously, all right? I don't think it's going to hurt me very much.
This does not depend if you change the same class.
Yeah.
I mean, the torsoric set depends, but not the set. So
yeah, everything is fine, yes. Yeah, whatever. Okay, so this is a setup for any field. You can do that, but things get interesting when we start looking at the local global obstructions, and so we can consider then the following thing, which is a set which is slightly bigger than that, which is the union. Let me write this down over the same. So still global twists of this group of now, but looking at the image of these maps of YC of the adeles of K, and that, well, certainly this contains this, so it contains xk, and this is a subset of the points of the adelic points of X, which I'm going to denote like this, and is the set of points of adelic points of X which are obstructed by this cover. And so this is a set smaller than this. And we would hope to, so we were sort of sandwiching we're trying to narrow down the rational points by picking up a slightly smaller set that's smaller than the set of rational points. And the other thing we can do is which is the descent obstructions, is vary now pi in some family F, which I'm not going to specify, and look at those. And, well, this still contains a set of rational points, and if this family is rich enough, we may hope that we narrow down the set of rational points or constrain the set of rational points. And sometimes we can even prove that it is empty and therefore conclude that that is empty. That's when there is a descent obstruction to the Hasse principle. Okay, so I'm not going to try and give examples of this, but I want to mention one case which inspires some of the stuff that I'm going to talk about, which is a theorem that Harari and I proved a few years ago, is that if K has characteristic P and X is affine, and F is the family of covers Z to the Q minus Z, where Q is some power of the characteristic, equals F, where F is some regular function on X. So you're going to have to vary all the F's, take all the F's in the regular functions.
And G
is the FQ, yes. But I'm going to vary Q as well. So I have to allow all powers of the characteristic. So the G's are varying as well. I didn't mean to say there that I fix a G. I may allow myself many G's. So if you take the family of covers where Q is some power of P, powers of P, and F, so this is the family, then this intersection is exactly the rational points. It's a very surprising thing because, I don't know, a very strong result. The proof is not super difficult. It boils down to the Riemann-Roch theorem at some point, but the result is surprising in a way. And but this is I guess I need little k to be finite, maybe. Well, let me just put that for guarantees. But the cardinality of little k is not this q. So the q has to vary over all powers of p for this term to hold. And I wanted to find something similar to this in other contexts. So I'd love to find something similar to that over number fields.
So what about non-affine varieties? Is it false, or you can't prove it?
So it's completely false. Yes. So there aren't enough functions, and there may not be enough covers. So yeah. So yes. But so when I move on to my next thing, which is going to be an analog of this, we'll see. I'll give some examples of what happens in the non-affine case, and then we'll discuss exactly that. So okay. So that's. Is it okay to do that? Put it up there. And okay, so I don't have anything to say for number fields. So now I'm going to cross out number fields from the talk. But I want to find an analog at. And so, like I said, the torsors are torsors. The group is FQ. So it's the group of constants. And, well, we'd like to try and do something over function fields, maybe over the complex numbers, over fields of characteristic 0. But now we cannot represent the constants by a finite group scheme. But we can talk about the constants form a group. And in fact, torsors under the group of constants is the first example of torsors we learn in mathematics. So when you study calculus, right? So the integral of x squared, as we teach our students, is that, right? And what is the c? C here means that the antiderivative of x squared is a torsor over the constants. There's not a single antiderivative. It's a torsor. And it's exactly what I want to do. So I want to represent I want to study differential equations. I want to look at integration as defining a torsor over the constants and try and study the Fontane equations over function fields from the point of view of calculus, if you like. So, let's start with, so you can look at, so you fix x a variety. Well, let's start with x affine over k. And k is a function field, so this setup here. And we can look at, k has a derivation. So k is a function field, so let me write it over here. So k over little k of t, so choose t in k is finite separable. And I'm going to denote by delta the derivation ddt. So differentiation with respect to t, which is so k has a derivation delta.
Which you extend to capital K.
Yeah, I extend the derivation to capital K, yes. Uniquely, because it's a separable extension. Extended. And way over there, I want to look at equations delta z equals f. So I want to view this, and now f is just like there, for now, is a regular function on x. So my x is affine to begin with, so we can take regular functions on f, and we can look at this. Now this is not an algebraic object, it's a differential. I mean, there's many ways of formalizing this. For the next few minutes, I'm just going to take it informally, and then later on I'll try and put it in a sort of a coherent setup. But you can ask the same question. We can look at, so what are the torsors, or the twists of this cover? The twists of this cover is like in calculus, right? So the twists are delta z equals f plus c. Where C is, well, C is in the constants for the derivation, which, you know, if in characteristic 0 is the actual constants, and characteristic P is the P's powers, but we'll just say that. So these are the twists of the cover. So this is Y, and I'm not sure yet where Y lives, but lives somewhere. But these are YC twists of y, well, y to x. And we can ask, okay, well, so what would be the question? So look at the points. So what is going to be x, ak, pi is the set of points p, adelic points. So I'm going to write it very explicitly, such that there exists a C in K. So I want to look at global twists. So I'm looking at the global twists of the cover. So those global twists, C in K, such that for all place V, place of K, there exists a ZV in capital KV, such that delta ZV is f of PV. So P is a point, an adelic point, so has coordinates PV plus C. Huh? Yes, delta, yeah, so yeah, okay, so maybe, yes, in curve delta. No, yes. No. No, that's not what I want. Yes, no, I want. Oh, these are twists, yeah. Because they're global twists. I mean, if the C is constant, then there's the same. Yeah? Huh?
The set should be added by the constant and not f, right?
Huh?
You're having a derivative and not the antiderivative.
Yeah, I have, well, if I change, yeah, the z changes by a constant, yes. So huh? Yeah, so my analogy is a little messed up. So yeah, because if I can integrate c, I can pull it back in here, right? And then it's the same cover. So c is actually in k mod, yeah, so c is a class in k mod delta k. So here's the thing. So this is the H1. This is the H1. So the constant, okay, let me write down something in terms of group schemes that I'm going to try and formalize. So there is a map from the additive group to the additive group, which is delta, and hopefully it's surjective in some, once you extend the coefficients big enough, and then there's a kernel, which is the constants, right? So these are the things that have derivative 0. And so, you know, if such a thing exists in some setup, then you should get that H1 k GA delta is GAK mod delta GAK, which is k mod delta k. Assuming we can make sense of this. But that's, yeah, so the constants give you the group scheme, but what you really want to use to parameterize torsors is the H1. So this is the H1k GA delta. So this is x in GA, delta x equals 0. Okay, so now things are better. And we have this. And the theorem I can prove is that, so now the only thing that varies is f, right? So the cover is given by this. F is a fixed choice of a regular function. And I can prove the theorem, which is, the proof is very similar to my theorem with hierarchy, that the intersection over pi, so there's varying f in kx of x a k pi is exactly xk for affine varieties. And this can be formulated in a purely, you know, the formulation is here. So this is completely elementary. You know, this is a sort of a motivation. The statement, you know, this can be, you know, formally define the set like this, and then this theorem holds. Okay? Now, Tomasz asked the right question, which is what do you do if the variety is not affine? So to deal with that, I want to be more precise about, you know, things like this and functions. So what is this thing? So this is not a function. This is not a variety. This is some other object in some other category. So I want to. So how does this work? Which one is it? Aha. Am I doing this right? Okay, so I want to define what are called jet spaces. So let me first define, so x, so let's start with x affine. and write x as, I don't know, spec of k x1 xn modulo f1 fm. Okay, and I want to define a scheme x1, which is going to be spec of k x1 xn y1 yn. So you double the number of variables, and then you mod out by the polynomial ring generated by, or the ideal generated by these guys, plus what you get when you differentiate something like that. So I've got, the f's are in x. So the f's are in x. The y's are going to appear explicitly in a moment. So right now the f's are in f, and then I'm going to put in something like df1 dx1 y1 plus df1, well, gxn yn plus what I'm going to call f to the delta, f1 to the delta. And this is the polynomial you get from f1 by differentiating the coefficients. Okay? So this is what you get when you differentiate the equation, this equation. So if you take df1 and you apply the chain rule, you get something like this, where, so this is going to be sum of df dxi at some point a, delta ai plus f delta of a, right? So this is the chain rule applied to the polynomial f. And so I want to put those guys here, and then the same thing with y1 to yn, thank you, plus fm delta. Okay? So this is an ideal, this is some polynomials, this is an ideal, I mod this out. So this is a variety, an affine variety over K in some bigger affine space. So this is an n-dimensional space, this is in 2 n-dimensional space. And the nice thing is that if you have a point A in xk, then you have then there is a point, which I'm going to call nabla A, which is given by coordinates A and 1 am, delta A1, delta am, belongs to x1 of k. So this variety was designed so that there is a map from rational points in x to rational points in x1. K rational points. Yes? Is it possible to say what unpaired x1 represents? I mean, it looks a little bit like a yeah, it looks like a little like there's. Not offhand, no. I've been asked this question before. I don't normally think that in this term, so I haven't really tried to figure it out. So you describe all the k points of x1? Well, the solutions of these equations? Huh? Yeah, I'm sure it can be done. I don't know the answer offhand. Okay, so what I was trying, but this construction is, so I guess Bjorn is asking this because he wants something functorial, and this thing is nice and functorial, and you can define, so this is a nice functorial, you can define x1 from x for any variety by covering it x in affine patches and doing this construction affinely and gluing. So x1 is defined for any x. Doesn't have to be affine. That's the description of an affine case. And then you can iterate. So you can define x2, x3, and so on, higher derivatives, and xn, and x1, x2, etc. And you can even define an x infinity, which is not a scheme of finite type anymore, but is still something, x infinity. And yes. Yeah, so there's the map from x1 to x. This is a nice map of varieties, right? So this is projection on the first n coordinates, right? So this guy lives in a affine 2n space, and if you project onto those coordinates, you get this map. So this is a nice map of algebraic varieties. This map here is not a map of algebraic varieties, but it's good. All right. So now on x infinity, now I need to do two things. So I want to pass from x to x infinity to have more functions. So now I can talk about, so functions in x1, I can think of as being functions on x that depends on the variables and the first derivatives of the variables. And likewise, the functions in x2 are functions that depend on the variables, the first and second derivatives, and so on. So now I can talk about what's called differential algebraic functions. So functions defined as variety in terms of the points and their derivatives.
Maybe this is the same question as Bjorn. Can you say something about the structure of the fibers of the map?
Yeah, so for x1 to x, this is a torsor for the tangent bundle. It's not the trivial torsor because of this guy, right? So if this guy wasn't there, so for example, if the polynomial, if the coefficients are constant, then this thing vanishes, and then the x1 is just a tangent bundle. Okay, so. Yes, yeah, x1, and the higher x is a sort of iteratively over that. Okay, so now I can do exactly what I was doing, but in general I can look at. So maybe I'll move this up, move this one back down. And but now I can't just look at regular functions because there may not be any regular functions. So I go to this ring, which is sometimes denoted like this, which by definition is maybe k of x infinity. Regular functions on x infinity. Now there may be some, there may not be. So we still have the question, so what is x infinity and does it have functions? But if it does have any functions, I can do this. And but now I don't have this theorem. Yes. Huh? Yes. Yes. Yeah, that's all what it is, yes. So these are functions in the coordinates and some derivatives up to a certain point. Yeah, finite and many derivatives. And I can look at this and I can try and figure out what this is. And well, it depends on the variety now. And but in some cases I can say something and okay, so here's a theorem. So if x over k is a projective curve, smooth projective curve, smooth curve of genus G at least 2, such that the Kodaira-Spencer class is not 0, so it means that it's varying in moduli, that's all it means. So if you think of it as a family of curves, it's varying in moduli, then you recover the rational points using this differential descent obstruction. And the proof is, I mean, This is an easy corollary of the previous theorem. The proof is that x1, so you only need a differential function of the first order, x1 is affine. So this is a theorem of Guillaume in characteristic 0, and Guillaume and myself in characteristic P. So really you just pass from x to x1, you use the map nabla to pull points from x to x1. So if you have rational points in x, you pass the rational points in x1, and you can describe the rational points of the curve in terms of no. This construction is when x itself is affine, x1 is affine. The x1 is not always affine. When x is affine, I defined x1 as an affine scheme. When x is not affine, I have to cover x, by affine patches, define the x1 of each patch, and then glue. Okay? Any more questions? So x1 is not guaranteed to be affine, and in fact, if the curve is constant, it's not affine. So, right? Because when it's constant, it's the tangent bundle, and the tangent bundle is not an affine variety. So, what happens when x is constant? So x is defined over k, a smooth projective curve. And you look at x over k, to extend scalars to k, then x1 is not affine. But you can still ask, what is x1? What kind of regular functions does it have? And what do you get when you do this? And it's interesting. So you pick out, so you almost pick out the rational points. You pick out the rational points, so I'm not going to write it in detail because it's complicated to, but if you look at this guy, you're not going to be able to do anything with the constant points because the constant points have derivative 0, so you don't, this differential obstruction doesn't catch them. You're going to catch xk, and you're going to catch the union with the product, so adelic points for which the coordinates are constant. So little kv is the residue field of the function field at v. So I'm not assuming that the constant field is algebraically closed. If the constant field is algebraically closed, it's just xk. But you can have something like that. So I can take a product, so an adelic point, each coordinate is a constant point, but each component can be a different constant point. So this is not a global point. And this guy is going to be here. There's more. So those guys you can't distinguish from global points by the center obstructions. And there's something else, which is am I going to write this? So this is if x is hyperelliptic, you get something that is union product and v of so the collection of the things PV in PV equals P or IP, P global, and with involution so if you take a global point and now you make an adelic point where each component is either P or the image of P by the hyperelliptic involution. So you can sort of Pick the p and minus p if you want, on the Jacobian. So you can pick the signs in any way you like. So you construct an adelic point, a crazy adelic point. But it's going to come from a global point, but not really. It just sort of differs. And in the hyperelliptic case, this thing shows up in there. So if you don't, if you want to ignore a hyperelliptic, it's just it's just global points plus things which are constant, adelic constant points, if you like. So I don't know. So here's another example which huh? Yeah, genus at least 2, yes. Yeah. So always assuming that genus is at least 2. So I want to look now at the abelian varieties. Of some dimension g. So that's going to include the case of elliptic curves. So there's a map. There's a differential differential map. So it's a map of differential algebraic map. So it's a map in this category. So you have to go up to x. I think going up to x2g is enough. So you go to, you include some. So this is the Manin map that he used to prove the model conjecture for function fields. And he gives a map which is expressed in terms of the coordinates of the points and some of the derivatives that is from a affine space and is actually a homomorphism. And it turns out that if you look at the adelic points, it's defined in terms of the coefficients of the equations and their derivatives. So it's not a map in algebraic category. It's a map in this differential category. So you have to. So it's expressed polynomially, or as a rational function, in the coordinates of the points plus some derivatives of the coordinates of the points, and the coefficients of the map involves the coefficients of the equations defining f plus some of the derivatives. So if you want to describe this guy, so you can use this function. So the coordinates of this map are differential regular functions on x. And you can look at the torsors and the obstructions given by that. And what you get is a set of points for which the image is some vector space in here. So the image, so mu of this, if you like, is a finite dimensional little k vector space in, well, k to the g, if you like. So you don't get the rational points. You get something more. The capital A. Yeah, here, a fine space. Okay, yeah. Sorry, yeah, G-dimensional affine space. Maybe I should call it, yeah. Something like that. But no, I don't want to say that. I want to say affine space of dimension.
And then in the next one, you have two
Huh? No, pi is mu, yeah. Thank you. Yeah, so mu, so if I want to describe this, I'm not quite clear how I can sort of concisely describe this set, but the values of mu on this set end up, so the condition that locally an element here comes from points on the abelian variety constrains the value of mu to land, constrains the poles and so you get a finite dimensional vector space, which is already something money new, and it is important in his proof of the Mordell conjecture. So, if you think of an abelian variety as C to the G modulo a lattice, and you can think of an abelian variety over a function field as C to the G modulo a varying lattice, at least locally, right? So the rational points is going to be a finite rank Z submodule of C to the Z is going to be mapping to the rational points. What's happening is that this differential descent obstructions pick out the span of this Z module as a C vector space in there. So what you do with this differential descent obstruction, you can identify constants, but you cannot make the difference between an integer and a complex number. They both have derivative 0, so you get something like that. Now, I have a few minutes. I was being informal, and so my approach to this has been informal, but I've had a student looking at this from a more formal point of view. So he's been looking at huh?
What was the claim about the abelian varieties? What was the result?
Is that the mu is a finite, when you look at the points which are unobstructed by all the descents, I don't have quite a description for the points inside the abelian variety, but the image of it under mu is a finite dimensional vector space over the constants. That's, didn't I? It's there somewhere. Hang on a second. You complained about the mu, right? Yeah, so that line there, so yeah.
I'm posing this problem.
Yeah. So that thing, so inside the parentheses is the set of adelic points.
The finite dimensionality.
Yeah, the finite dimensionality is a very strong thing. And so you have to try and describe, so what you do is you pull back, you have to pull back under mu. So there exists a finite dimensional vector space, little k vector space inside of capital K to the G, so that the unobstructed points is the inverse image under mu of this finite dimensional vector space.
Connection between the dimension of this vector space and the right?
So it's, I want to say well, so there is a problem here. So it's like descent in an abelian variety. So what you happen here is this thing is like a Selma group, right? So there is the rational points go in. So I would like to say that this vector space is the complex span or the K span of the model V group, which would be the wonderful thing. But that may not be true. There may be a sort of Tate-Schaffer average thing. Okay, so. And there are also the possibility that points which are Z linearly independent, their images on the mu become C linearly dependent. So the rank may drop. So it's not entirely clear what's going on, but there's obviously a relation. There's obviously an exact sequence.
Does this extend to semi-abelian varieties?
Yes, probably, yeah.
Because the F1 case you say is...
Yeah. So for GM, there's this map, mu, that sends x to delta x over x. So it's logarithmic derivative. So So the statement about finite dimensionality is not when you take rational points, but when you take integral points. So if you take a set of integral points here for s integral points of some s, then you can say this is a finite rank group times the constants, and then when you take the logarithmic derivatives, you're going to get a finite dimensional vector space here. And then you can analyze the question here also. So that's a sort of a baby version of the money thing. Okay, so I wanted to mention some work in progress of my student Alessandro Macedo. So first thing that he did was to look at this. So you can formalize it. So you're working on x infinity. There are sheaves, or that makes the sense of this, and then you can talk about H1 x GA delta, and I guess this is
how do you make sense of that as sheaves? Can you explain that?
Well, the GA is just GA. Huh? So you're not working over K, you have to go to the differentially closed field containing K. So you have to work in x infinity of K, I don't know how I'm going to call this, So the differentially closed field containing K. So you have to solve all the differential equations. And then there's and then you can make sense of what so maybe, so this is well, it is kx infinity modulo, so this is going to be delta of kx infinity.
What's the hypothesis on x now?
Well, good question. Well, anyway, so we don't really need this to do what we did, but I wanted to bring up another which is taking logarithmic derivatives, and this so goes to GA, and under the right situation you have something like that, and now you get a more interesting long exact sequence which has something like kx over, so kx, this is the ring of regular functions on x infinity, and then you have d log, so this is d log, right? Call it d log of ks infinity star maps to the H1, and then there's a weird thing that I don't quite understand when we're sort of struggling with, which is some kind of, well, it's the H1 of GM. Yeah, so it's this term here. And we have an exact sequence like that. And so Macedo was looking, so this suggests to look at torsos, instead of looking at delta z equals f, to look at delta z over z equals f. And in the affine case, we can do this, and we're just looking at this part here of the cohomology. And he was able to show that looking at those differential equations and looking at torsos of that is also enough. So that if x is affine, the intersection over pi, so logarithmic of x, ak pi is xk. And so, but that's looking at just the global function, so it's just looking at this part of the H1, but the H1 has more stuff. And because the H1 has more stuff, we hope that we can treat these cases. So there are situations, non-affine situations, where you have more, if you just look at additive differential distance obstructions, we don't capture, you get more, you don't single out the rational points. By using this multiplicative differential distance obstructions, and perhaps using things which are locally like that, but not globally like that, so using this part, or using the full group here, we should be able to cut down the rational points, at least in situations we understand well, like, for example, curves or abelian varieties. But this is still ongoing, and I don't know where it's going to lead. So that's a good place to stop. Thank you.
Any questions for the speaker?
Have one? I think I don't need them.
In the affine case, is this group peak of x infinity always trivial, or is it just that this does not play any role in the obstruction?
I don't know. Yeah, it doesn't play any role, but I don't know if it's
maybe
trivial.
It could be non-trivial.
It could be
even
non-trivial,
in the
yes.
affine case. Okay.
You write it peak. Is it honest peak as defined as usual, or is it just some analogy?
Well, it's H1 of this. But it's H1 of x infinity GM. So it's...
But usual sense of algebraic geometry, or in a different...
In the differential, yeah. So I don't know exactly what it represents. Yeah.
Any other questions? Okay, let's thank the speaker again.
Thank you.